Good morning, students. Today we are going to discuss the topic Young's double slit experiment. So interference, already we have discussed basically the theory of interference, and the theory we are going to use it here. Now S is your source of light and S1, S2 are two coherent sources. It comes from a single source S. Now P is a point where the rays from S1 and S2 interfere and gives us the interference fringes. P is a point on the screen which is at a distance capital D from the slit, and O is the midpoint, and the slit S1 and S2 have a separation small d. So M to O is your distance d by 2 and O to N is your distance d by 2. P is a point where you are going to get the interference fringes, and it is at a distance x from the center O. Now in triangle S1MP, S1P square equal to S1M square plus MP square. So S1 using Pythagoras theorem. So S1M is your capital D, so D square plus MP is your x minus D by 2 whole square. So D square we are taking common, so within bracket 1 plus x minus D by 2 by capital D whole square. Now S1P square root if we take, then it comes out D within bracket 1 plus x minus D by 2 whole square, x minus D by 2 divided by capital D whole square, and with the exponent half. Now x minus D by 2 is smaller compared to capital D, as you have seen from the figure. So you can apply binomial expansion considering the terminating terms. So it's 1 plus x to the power n. If x is very less than 1, then it comes out to be 1 plus nx. So n is your half, and x whole thing is your x minus d by 2 by capital D whole square. So it comes out d within bracket 1 plus half x minus d by 2 capital D divided by D capital D whole square. So we have got S1P. Now similarly we can get S2P if you consider the triangle S2 and P. So S2P whole square equal to S2n square plus Pn square. So S2n is your D square and Pn is your x plus D by 2 whole square. So if we take D square common, so it comes out 1 plus x plus D by 2 divided by capital D whole square. Now if we take the square root, S2P equal to D within bracket 1 plus x plus D by 2 divided by capital D whole square to the power half. So if you are going to apply binomial expansion, then it comes out to be your S2P equal to D within bracket 1 plus half x plus D by 2 by capital D whole square. So we have got S2P as well as S1P. So we can define the path difference by taking the difference of S2P minus S1P. So S2P minus S1P, if we substitute the value, D comes out to be common, and within second bracket 1 plus half x plus D by 2 by capital D whole square, second bracket close, minus 1 plus half x minus D by 2 by capital D whole square, second bracket close. Just like we have substituted the terms S2P and S1P. Okay. Now if you take the 1 and minus 1 goes off, and 2 D square will comes out. So you do have only within the third bracket x plus D by 2 whole square minus x minus D by 2 whole square. So if we simplify, you will get 2 times of 2x D by 2. Other terms get cancelled. So D 2 goes off, 2 goes off, so x small d by capital D. So this is your path difference. Now for bright fringe or constructive interference, already we have defined the expression in our last class. The path difference is your n lambda, and varies from 0, 1 to like that. So in place of path difference, we can substitute x small d by capital D. So x comes out to be your n lambda capital D by small d. So if you substitute n equal to 0, then you will get x naught, that need n place of 0, it means 0. That is your central bright fringe. So n equal to 0 means x not equal to 0. So you see x is the distance from P to O. So if x goes to 0, then it is the point O. So at O you will get central bright fringe as per this expression. Then if you substitute n equal to 1, you will get first bright fringe, that is lambda capital D by small d. If you n equal to 2, then 2 lambda capital D by small d. So in this way we will get, so x2 minus x1, if we take the difference, 2 lambda capital D by small d minus lambda capital D by small d. So if you take the difference, it comes out lambda capital D by small d. So see x2 minus x1, x is nothing but the distance and p is your bright fringe. So in between, as per this figure, in between two bright fringe you will get one dark fringe, is not it? Central bright fringe, first bright fringe, first dark fringe, second bright fringe. So if second bright fringe and first bright fringe you will consider, then within this you will get a dark fringe. So width of the dark fringe can be defined by taking the difference of x2 minus x1, that is your dark fringe width. And dark fringe width comes out to be a lambda capital D by small d, and it can be symbolized by the symbol beta. So sometime in exam it is asked to define the fringe width or the expression or the numericals. So lambda capital D by small d is provided. Now for dark fringe, again destructive interference already we have defined. Part difference is here 2n minus 1 lambda by 2. So you check out the previous class, x small d by capital D, 2n minus 1 lambda by 2. So x comes out to be your 2n minus 1 lambda capital D by 2 small d. So n is your 1, 2, 3, like that it goes off. So if we substitute n equal to 1, then you will get first dark fringe, that is lambda capital D by 2d. If you substitute n equal to 1 here, lambda capital D by 2d. And n equal to 2, if you substitute, then 3 lambda capital D by 2d. So n equal to 3, so 6 minus 1, 5 lambda capital D by 2d. So x1 is your first dark fringe, x2 is your second dark fringe, and x3 is your third dark fringe. So if you take the difference between two dark fringe, you will get just like this one. Difference between two dark fringe gives you the bright fringe width. So 3 lambda capital D by 2d minus lambda capital D by 2d. So it comes out to be your lambda capital D by small d. So you can take any consecutive difference, you will get the fringe width. If you go for the constructive interference, individual difference, that is your dark fringe width. If you go for the destructive interference, the individual difference, consecutive difference gives you the bright fringe width. So bright fringe width is your lambda capital D by small d. So you have seen that in dark fringe width and bright fringe width, both have the identical value. This is your dark fringe width, lambda capital D by small d, and this is your bright fringe width, lambda capital D by small d. And you see this figure, P is a point. So you see at O you will get a central bright fringe, and the shaded part we are trying to show, that is your dark, that is the first dark, then first bright, then second dark, second bright. Like this it will go up, and similar way it goes in down also. So there is an alternate dark and bright fringe you will get in interference pattern. So please go through this topic. This topic is very important, and numerical used to come from the expression. So it's a simple, only the figure you must have to go through, and the simple geometry, Pythagoras theorem, and simplification, binomials theorem. So this is all about. Thank you.